Thank you for the opportunity to give an overview. This will follow the previous talk in many respects. We're going to be talking about using AFM FTIR to look at impact events and space weathering. But in this case, the radiation field is we're looking at actual lunar samples. Work is done by Adam Grice, who's a graduate student in the physics department at the University of Georgia. Phil Stantz was an astronomer, faculty member there. Johannes Abadi is a solid state physicist. And then his group members also contributed. And then Michael Schreibel and Carl Lang and myself at Georgia Tech were involved in this. Okay. All right, so the lunar samples we've looked at were Apollo 15 samples in a brusher with a shock norite and spinel tractolite class. These were thought to be ejected from the Imbrian Basin. They had a lot of exposure, so we chose these particular samples because they have been exposed. We were looking for space weathering signatures. One thing that's pretty important is we have like 0.307 and 0.311. So when we asked for these samples, we had them shave off a sliver of the solar wind facing rim. And so one is the exterior surface, that would be the solar wind facing one. And then we have a sliver of the interior. We also have an ilmenite Apollo 12 sample, and this is all, has abundant micrometeorite pits, remnants of glass, really been bombarded. And again, we had two pieces of it, an exterior and interior flake. So we're going to look at these very specifically, and then we're going to use the technique that was just discussed. And we're going to do nanoscale Fourier transform infrared spectroscopy. But this inherently means that we have to have a system that breaks the diffraction limit. We're going to do FTIR spectroscopy, which is micron scale wavelengths, but we're going to do this with nanometer scale resolution spatially. And so you do this by beating the diffraction limit using an atomic force microscope. But this is spectacular because you can get real space mapping as well as full optical maps at the same time. And so you focus the laser and you look at this in the scattering mode, and you can get the spectroscopy. Then you can move this around and the cantilever will deflect. And is there a laser pointer? The cantilever will deflect, and then this deflection will be detected, and you can move this around and get a map. While you're getting a spatial map, you get a full spectroscopic map. This is not new. It's an older technology. In the 90s, actually, it was introduced, and it was used primarily by surface physicists. And they looked at very simple structures, and they were interested in the atomic and molecular structures of their samples. You can extract out vibrational frequencies, you can get phonon modes, you can get chemical information. There's another technique we used at the same time. It's scanning photoluminescence. So it's ostensibly the same technology, except for we don't use the scanning probe tip. You focus a higher energy laser beam or, in terms of its wavelength, and then you look at the luminescence, and then you can move that, and you can look at the spatially resolved photoluminescence. And that's very useful because it gives you information on electron traps and damaged sites. And those are typically correlated with the presence of impurities, such as ions that are known to be in these lunar materials, magnesium, iron, chromium, neodymium, et cetera. Okay, so we're going to look and use both of these, right? So on the top here, on the left, is the optical image of the Apollo 15 sample on a silicon oxide flake on a substrate. This is 100 microns. This is a very small region of it. This is sort of the atomic force topographical map. And the colors here only represent different spots. Okay, and you can see you can get a pretty similar photoluminescence spectra on many different areas within this interrogation zone. Okay, and you can give it a similar map, but in this case, E is looking at the near field amplitude map. So this is the photoluminescence, this is the near field amplitude map, and this is the Fourier, this is the FTIR, this is the infrared spectrum, and this is in the amplitude mode. And we just heard about this, so I really am happy about this because I'm trying to convince you that we made SiO2, or that SiO2 is on these made by the solar wind, right? So this is a perfect previous talk. So part 2 of her talk is this is formed as a solar, this is a signature of solar wind damage on the outside part, which is a silicate, and it's not on all of them. One of the things that you should note is that the amplitudes of these are different, right? So here's this feature here, there's this feature here, and the relative amplitudes are different. So we're going to try and understand what are the relative amplitudes mean? And you can do this for mapping the phase or mapping the amplitude. Okay, there's a lot of data on this slide, so I'm going to take a little bit of time on this. All right, so here is the photoluminescence spectra of both of these samples and all of the sides that we had. Well, this is the photoluminescence spectra that I showed you. The data is black, red is a fit, and then there's this blue simulation, which is relevant to this, and that's simulating the SiO2 feature, which is showing up here at 1100 wave numbers, which you told us it should be there. Okay, so these are looking similar, but the ones that are the inside flake, they have a feature here at about 850 nanometers. That correlates pretty well with the presence of neodymium. This big bump over here is correlated with the presence of chromium. So we see some signatures here which are related to chromium, neodymium, and it doesn't fit perfectly neodymium. And there is a paper out there that says this wavelength range can be correlated with electron traps. Okay, so it could be due to electron traps as well. Here's the amplitude spectra of all of these, and I already said this. So this is the feature we're going to care about. And it shows up a little bit on the Apollo 15 sample, but it's really prevalent on this sample here. And the question is, what is this? Well, we already know the answer. It's the silicon oxide. It's amorphous silica. We use a dielectric, the real component of the dielectric constant that was simulated. And this is sort of the SiO3 moiety that fits this extremely well. And then again, I said that there's changes in the ratios of some of these bands. So we're going to pay attention to that. This is the Christensen feature. This is the Ronson bands here. And we're going to try and understand what these band ratios changes are telling us. So what we have is a topographical map like it was demonstrated. You can sort of, move this around and get a spectra and sort of, spectroscopically resolve this and topographically resolve this. There's a pretty interesting paper out there. There's a couple of papers by Martin where he says, or they say that this 1050 to 932 ratio may indicate shock-induced effects. And I'm like, okay, so let's look at that. So here's a force image, and then in the red zone and in the blue zone, we do an NANO-FTIR spectra. And you can see that the spectra you get is completely different. So this is the phase, this is the amplitude, and the red is different than the blue. All right, so these are giving us different information spatially. And then we said, well, let's just lock ourselves on to these features, which were in this paper, and do a map. And then we can get a full topographical map at 935 wave numbers, 932 wave numbers, and see what this is telling us. And you can see that the contrast difference, so this is amplitude maps, this is phase map, amplitude map, phase map, different frequency. But they tell us that the contrast between these data sets is different. And in fact, the contrast between the 1050 wave number feature is stronger than the 932 wave number feature. So we are interpreting this in agreement with this group that this could be a signature of shock metamorphism locally. So we said, okay, well, that's nice and interesting. And so but it can't just be on one spot. Now that's the problem with this AFM locally in samples, because you're only looking at a very small spot. So the more spots you can look at, the better. So we looked at a few other spots and we see basically the same thing, but a different zone. Ostensibly the same. There are clear contrast differences between these. And so we say, well, what does it mean? So in using the pressure regimes that you can extract from this paper by Martin, you can replot this, and it's the ratio, the 1050 to 935 ratio versus 935, and you can look at it and bin them with respect to the ratios that are correlated with the pressure that came from this paper. And you see that there's, in this sample here, these are all clustering less than 25 gigapascals. This zone here, in terms of the ratio, is correlated with 25 to 45. And then there's this high pressure zone above that. The other side of the sample is different. The inside of the sample, the outside sample is different. They're all clustering right around here. These are lower pressures, these are higher pressures, and then you have a bunch that are going into pretty high pressures. And so then you can recalculate this or take these amplitude ratios and then plot them on a topographical map. And you can see that you have these damaged zones. So this is on a micron scale, less than a micron. So you have this 100 nanometer scale zones of severe damage, right? And so we're interpreting this as a very localized shock fronts or damage fronts that may be representative of different pressure zones that may have come from local impact events. So on that, I'm going to just give you some concluding statements or suggestions, right? So you can believe me or not, but I think you will believe me based on her work, at least with respect to the 1150 wave feature. Okay, so the ilmenite basalt and impact pressure, they show evidence of intrinsic or delivered neodymium and amorphous silicate glass component on the exterior surfaces. There's some intrinsic chromium and then, trapped electron states, which is limited to the interior of the surface. So these are probably made by X-rays or penetrating radiation. There's a spatially localized feature band ratio that we are interpreting as shock-induced nanostructures. And the shifts in these band positions do indicate accumulated damage. Doesn't have to be radiation damage, it could be micrometeorite damage. And if you know this and you know the fluxes, you could try to use this to back out mechanisms for damage and then use this to look at surface exposure and age, and then radiometric dating. So long term, we want to correlate this with radiometric dating. And then I'm going to stop. I probably went over a minute or two. Sorry about that.